In lab last week, we used resistive dividers and capacitive dividers. In lab this week, we're going to combine these, where we'll have a voltage divider that consists of both a resistor and a capacitor. Now, to analyze the output of this is a little bit more complicated. We will have an input sine wave with some voltage peak to peak. And you could do this with VRMS or V peak to peak. It's a little bit easier to measure peak to peak, so we'll deal with that. And we'll have some peak to peak on the output. Well, if we recall last week, if we do this with two resistors that are identical or two capacitors that are identical, it just gives us a half height output, a half peak to peak output. But that's just talking about the amplitude. There's also a phase angle, and that describes whether or not the output voltage is leading or lagging the input voltage. And so to do a full analysis of this, we're going to use some complex numbers. And so what that means is instead of just talking about resistance capacitance, we're going to talk about impedance. So I'm going to call the impedance of my resistor here Z1 and the impedance of my capacitor Z2. And we're going to look at the resistor has purely real impedance. Z1 will be equal to R. And since it's purely real, it's at an angle of 0 degrees. And this notation here is something that shows up a lot, this angle notation. Z2 for our capacitor, well, a capacitor has reactance, and you will see different ways of expressing this. Sometimes you'll see the imaginary part included in the reactance, sometimes it will not be included in the reactance. In this class, we're including it in the reactance. So this is just going to be the reactance XC of the capacitor, which is going to be 1 over I omega C. And remember that 1 over I, the imaginary number, is the same as negative I, so I can write this as negative I over omega C. And the other way to write this using our angle notation would be to say that this is a reactance of 1 over omega C at an angle of negative 90 degrees. Where do we get the negative 90? That comes from the fact that we're treating our imaginary axis as the y-axis of our graph and the real axis as the x-axis. And so just think of vectors. If I have a negative y component and I start measuring my angle from the positive x-axis, negative 90 degrees would be 90 degrees clockwise from the positive x-axis, which would be in the negative I direction. So we want to figure out, all right, this V out. Well, Ohm's law still applies in its slightly more complex form. So the voltage across the capacitor is going to be equal to the current through the capacitor times the impedance of the capacitor. Well, now this current is a function of time, and this voltage is a function of time. And this impedance now has this complex component to it. So the first thing we're going to need to do is figure out I, because we already know what Z2 is from up here. So to figure out I, well, if this was just a resistive circuit, I would just combine R1 plus R2, and then I would say that the current through this is the input voltage divided by that resistance, and that would give me my current. And I'm effectively going to do the same thing here, just we have to worry about the angle as well as the magnitude. So the equivalent impedance is the resistance plus the reactance, or if I want to write this in complex form, that would be R plus our negative I over omega C. And if I look at this, if I think about adding vectors together, we could think of this as being in the x direction. This part is in the y direction, the negative y direction. I can't just directly add vectors like that. So when I'm adding together vectors, I find the magnitude by doing the Pythagorean theorem, and I find the angle by doing inverse tangent. So I'm going to do a similar thing here. And if we look at our phase diagram, I have a resistance along this axis, R, and then along my negative y-axis, I have my reactance, the magnitude of my reactance, 1 over omega c, and so my combination of those would be a vector in this direction where we're going to define our angle phi as coming from the positive x-axis. So, well, if I want to find the length of that, I do the Pythagorean theorem. Now, when I am finding the equivalent here, the magnitude of the equivalent, the length of that arrow, when I'm doing complex numbers, I'm actually going to be doing the square root of z equivalent star times z equivalent, where star is the complex conjugate, which just means we replace I with negative I. And so that gets me the square root of omega c to the negative 2, because it's that 1 over, plus r squared. So here I have the magnitude, and I just kind of flip them around here. The magnitude of my impedance, the angle of my impedance is going to be the inverse tangent of opposite over adjacent, but remember it's negative. It's in the negative direction from the x-axis, so negative inverse tangent of my opposite is my reactance, 1 over omega c over r. Simplify down, I get negative inverse tangent of 1 over omega rc. All right, so I now have the magnitude of my impedance and the angle of my impedance. So to find the current, well, we said before the current is going to be equal to, from Ohm's law, V in divided by the equivalent impedance. And V in we'll just say is at an angle of 0 degrees, just our reference. And here our equivalent impedance, we have a magnitude, omega c to the negative 2 plus r squared, at an angle of negative inverse tan 1 over omega rc. And when I do division like this, if you look in your book, you'll see a whole page giving you a quick table of how to do these sorts of divisions. Well, what I'm just going to do is subtract my angles. I just do this division, and so I get that my current is equal to V in divided by the square root of omega c to the negative 2 plus r squared at an angle of 0 minus my negative tan. So I end up with a positive inverse tangent of 1 over omega rc. So this is my current, the magnitude of my current, and the angle of my current. Now, I just take this whole thing here, and I plug it back into my Ohm's law to find the voltage across my capacitor. We're calling that Z2 is 1 over I omega c. So I get that V out is equal to this guy times this guy, V in over the square root of omega c to the negative 2 plus r squared times 1 over omega c, and recall that I'm not putting the I here because I'm just looking at the magnitude. The angle is going to go out here. This is at an angle of negative 90 degrees. When I multiply, so here when I did the division, I subtracted the angles. When I multiply up here, I'm going to add my angles. So the angle of this guy, plus the angle of this, my negative 90. And so I have that my voltage output has a phase angle of the inverse tan of 1 over omega RC minus 90 degrees. Okay, so if I do a little bit of simplification, I have a 1 over omega c here. Well, omega c is the same as the square root of omega c squared. If I multiply through by the square root of omega c squared, that cancels out here and leaves me with an r omega c squared there. And so I say that V out is equal to V in over the square root of 1 plus omega RC quantity squared at an angle of tan inverse 1 over omega RC minus 90 degrees. Of course, recalling that omega is equal to 2 pi f. And if we notice here, I see that the magnitude V out is dependent on my frequency. As the frequency increases, the magnitude of my output voltage decreases, and vice versa. A particularly interesting situation arises when I let omega equal 1 over RC. I end up with just a 1 here. I end up with a 1 here. Well, inverse tangent of 1 inverse tangent of 1 gets me 45 degrees. 45 degrees minus 90 degrees, I end up with negative 45 degrees. So if I have a angular frequency of 1 over RC, I end up with a phase angle of 45 degrees. So my output voltage here is 45 degrees off from my input. And negative 45 degrees, what does that mean? Negative means it lags. So that means if I am looking at the output, and I have two signals like this, let's say I have my other signal looks like this. As I'm coming from the left, I hit the blue one first, that peak first, and then I hit the green peak. So the blue peak came first, that green signal would lag the blue signal, the green signal would be like our output voltage with a negative phase angle. If our output voltage had a positive phase angle, then we would encounter its peak first, it would lead the input voltage.